All right, so here we go on chapter 17, the first two examples for the worksheets you'll be doing. Remember, these are Bernoulli trials, success or failure, and you first need to know whether you're dealing with a binomial or a geometric model. The first example here is giving me the information of a p-value that you either prefer to sleep, success, or watch movies or read on a long flight. So that would be what we call our failure. But our success is p equals 0.8. Now, when I look at randomly selecting 25 passengers, that gives me an n. And once I have an n value, number of trials, I know this is a binomial problem. So binomial problems are always named and modeled with NP, okay? So 25.8. Now, what I do now is I go into, is it a PDF or a CDF on the calculator? Remember, PDF is precise, exact, perfect, and that's what A says right here. We want exactly 12. So we're going to do binomial PDF, and in the calculator, if you have the prompts, it goes in the same order, but it's going to be N, P, and X, and in this case our X is exactly 12 prefer to sleep. Now the buttons on your calculator are going to be second vars is where you are going to find the binomial PDF. So if you head up on the calculator, once you hit second vars, you're going to go to A. Enter in your trials, 25, your probability, 0.8, and then your X value of 12. And this one gives us a value of, 2.97927, or 928 if I round up. But you'll notice over to the right on your calculator it says e to the negative 4. That is scientific notation of 10 to the negative 4 power. So my answer for this one, I move the decimal 4 times to the left because it's negative. So it's 0.000, and I'll just round up to 3. So it's a very small chance that exactly 12 are going to say that they prefer sleeping. So that is for A. For B, sorry about the messy writing, I'm writing with my finger here. The probability that all passengers, okay, so this is all 25 of them prefer to sleep. Again, it's exact. So it's binomial, PDF, and we are going to enter in 25.8 and 25. Okay, so second vars, all you have to change is the X value. And this one, the probability is still small, but higher. So it's 0.004. So less than 1% of the time are we going to see that all the passengers would say that they like to sleep on a long flight. Now, C says at least. Okay? At least is a little bit different. The at least model means that it has to be 20, 21, 22, all the way to 25. We're going to add all those up. Our calculator will do it for us using CDF, but the thing is it can't count up from 20. We have to eliminate everything up to 20. So for C, remember probabilities add to 1, so we're going to do 1 minus binomial CDF, and we're going to do 25.8 and 19, because I want 20 to be included because it said at least 20, so that means it could be 20. So enter it all in your calculator at once. 1 minus second vars, go to binomial CDF, and we're going to have 25.8, 19. We paste that in, and there is a 61.7% chance that at least 20 are going to say that they prefer to sleep. Now, lastly, we need to talk about the model, just the standard deviation and the mean, okay? So the average number of passengers is the mean. I'll put this up at the top here. So for a binomial, the mean is NP, so this is going to be 25 times 0.8, and the answer is 20 passengers, or what we expect, or who we would expect to say they prefer to sleep. The standard deviation is the square root of NPQ. So when you do 25 times 0.8 times 0.2, that is going to be 16. Then you take, so NP I already have, so that's 20. Just so you know, Q is 0.2, okay? So 20 times 0.2 is going to be 4, but it's under a square root, so the square root of 4 is 2. Okay, so our standard deviation is 2 for this problem. Now, on to the next problem. For this one, this is a geometric, and the way I know that is I don't know how many times I need to throw the ball to Sophie, because it says we're going to define X as the number of tosses until she catches the ball. So that's a success, and once she does that, we're done. So I do need to know my p-value of 0.1, the probability she will catch it on her second try, precisely her second try. So this is going to be a geometric PDF, okay? And then what we do for geometric PDF is we just enter in the probability and the X value. Okay, so P and X. There's no N. So if there is no N, you know that you're dealing with geometric. It's just for success. So again, it's under second vars. We're going to do geometric PDF, probability 0.1, catching it on her second try, and we expect that that's going to happen 9% of the time. Okay. For B, it says, what's the probability it takes more than 3 tosses? Well, our calculator can't count above 3. It can only count up to 3. That's how the CDF works. So more than 3 means it's going to take her 4, 5, 6, 7, 8, 9, 10, or so on. So that's a geometric CDF. Okay. And the geometric CDF is going to be, now this time we're not going to drop down 1 like the at least. We're actually going to go all the way to the 3, because it says it has to be more than 3, not at least 3. Okay, so more than, if I do geometric CDF, 0.1, 3, okay, that came out to 0.271. But remember, that's what we're eliminating, so it's 1 minus 0.271. You could have done 1 minus the second distribution, go to CDF, and enter all that in, and you'll go directly to your answer about 0.729. So 72.9% of the time, it's going to take her more than 3 catches to catch the ball. Now the last one, expected number. Again, that's a mean. But because it's a geometric, the mean is 1 over p. So that's 1 divided by 0.1, and that is going to be 10. So we expect it takes Sophie 10 tries before she catches the ball the first time. The next video goes on to examples 3 and 4, and then you can get started on the worksheet you have for class.